My name is Dr. Farhan Riaz, and this is the computer vision course that I'm teaching at the National University of Sciences and Technology. I'm using the slides that have been prepared by Professor James Hayes as part of computer vision course that is being offered at Georgia Tech University. Let's now move on to the next very important topic, and this topic is interest points and corners. This topic has a great significance when it comes to computer vision because many applications actually require us to detect all these interest points and corners and feature points. So we can what we usually do is that, for example, if you can have a look at this figure, we have a signboard that says stop, and if we want to do matching of the points or matching of the image regions or the patches, or if we want to match the edges or the regions across different images, so we can actually find some salient features or some salient image patches which are present in the images and try to match them. And this is called as the correspondence across different views in case of the images. Well, another example is the estimation of fundamental matrix that corresponds to two different views when we are comparing two different images. For example, in this case, you can see the two images, one on the left hand side, one on the right hand side. These are basically views, different views from which the images have been captured of exactly the same scene, the same person. And how can we do this point correspondence? We actually try to find out some points, for example, these specific locations. Then we try to locate the eyes or points that correspond to the eyes, and then we try to match all these points in the second image, and effectively we can actually calculate a matrix called as a fundamental matrix that can be used in order to transform one image to the other. So this is what we can do, and there are several applications at the end which can be done using these interest points. For example, we can do the image alignment, as we have seen in the previous slide. We can do that. Then we can do the 3D reconstruction of the images. We can do the motion tracking. We can do the robot navigation. We can do indexing and database retrieval. We can do object recognition. So you can see there are different applications, a very wide range of applications related to computer vision that can actually be implemented if we know about the interest points and corners. So the main question over here is what are the interest points? So let us suppose that you have to click on some point, and then you turn off your screen, you go base somewhere, and then come back afterwards, and you have a look at a deformed version of the same image. As you can see, there has been some, this is the original image, and this image has undergone some transformations. It has deformed to give us this image, and then we will try to always click on the same points. So which points will we choose in this case? So this is an important question. So in this case, let us assume that we have clicked at this particular point, and then once we come back after some time, we want to continue and try to identify the same point over here. Well, practically that would not be possible, and this is why we would never call it the interest point. On the other hand, if we, for example, click in the original image at this particular location, and in this particular image, it is easy for us to identify the same point. And if we want to identify another interest point, probably this is the point that we will once again find out. And if we know that this time, if we have tried to identify this point, once we close the lid of the laptop and come back and open the laptop again, we would know that we have to start off from this point. So that's why we can call it the interest point, and this is the significance of all these interest points that we calculate in computer vision. This slide gives an overview of how the key point matching can take place. So as we can see, there are several steps which are involved in this for implementing this entire procedure. First of all, we find a set of distinctive key points, and this is done by the extraction of the interest points, as we have seen in the previous slide. And then after we have found the distinctive key points, then we define a region around each key point. So we are not just considering one interest point because it might not be having any significance, but actually a region around the key point or the interest point is of high significance. Then the next step, the step number 3 that we do is that we compute a local descriptor from the normalized region. So effectively, we have to perform the normalization, and then we basically calculate a local descriptor that corresponds to that specific region that we have selected. And then once we want to perform the matching, we do this by the comparison of local descriptors that we have found out using key points and the regions in 2 different images. As we have seen in this case, all these interest points A1, A2, A3, they have been found, and then the interest points in the second image have been found, B1, B2, and B3. A2 corresponds to B2, therefore we draw a small box around A2, a small box around B2. We calculate the local descriptors corresponding to both of these regions, and then we can perform a matching of the local descriptors that we have found. And the main goal when we are trying to define these key points is that we have to detect the points that are repeatable and distinctive. So repetitively, if we can apply the algorithms and keep finding out the same point, that is very important. And the second thing is that all the points have to be distinctive. So these are the 2 important goals that we intend to keep in mind while we are trying to define the key points. And as far as the local features are concerned, one important requirement for these features is that they should be invariant local features. The invariance in terms of translation, rotation, and scale changes in different imaging parameters in the images. The need for the invariant features actually arises from the fact that an image can be transformed. It can be rotated. It can be scaled as using different parameters, and there is always the problem of perspective viewing. And due to this perspective viewing, we always want to obtain the local features for a particular image region, which are invariant to any kind of transformations that are taking place in the images. Well, if these features are not invariant, matching is not a simple problem anymore, because we are going to get different features for the same image regions, or and that creates a bigger problem for us. So this is an important requirement, that the features should be rotation, scale, and translation invariant. Well, we have another important application. It is panorama switching, where we would need to perform the exact same procedure. For example, in this case, we have 2 different images, and we know that there is this image and this image, and this part in this image corresponds to this region in the image. And if we need to stitch both of these images, we would need to have some strategy. So what we can basically do is that we first of all identify the interest points. After the identification of the interest points, we can extract feature vectors, basically a descriptor that is surrounding the regions of interest that we have selected, and then we can do a one-to-one matching between these points, and try to find out which point corresponds to which one. So there are some characteristics, once again, just to reinforce the requirement of all these properties of the interest points. They should be repeatable, which means that the same feature can be found in several images despite geometric and photometric transformations. So the need for invariance can be seen over here. Then there should be saliency, which means that each feature is distinctive. Then we should be keeping in mind that the features are compact and they are efficient, because if the features are not compact and the efficiency is not good, then this means that we are spending too much computational resource into doing this thing, and the locality, which is that a feature occupies a relatively small area of the image and is robust to clutter and occlusion.